Good morning and welcome to this next lecture on vibrations of plates and shells. Before we continue, right at the outset I wanted to make some comments. Somewhere down the derivation we had this term here, ds dash squared was equal to the sum of these terms, of which I dropped this term and I said this is a differential, this is a differential, this is a differential, this is a product of three differentials, okay, whereas this was a product of two differentials. So I would like to clarify that here also this is a change, okay, this is a change and there are two differentials here, okay, whereas this is a differential change and this is a differential change. There are only two differential changes here, whereas there are indeed three here and three here. So why did I drop this one and not that one? Compared to d alpha I, d xi I is a smaller change, okay. So this is d xi I, okay, there is one d xi I, okay, and here there is one d alpha I, so slightly bigger. Now here also there is a d alpha I, that is fine, and here there is another d alpha I, that is okay, okay. Now next both these are equal, okay, this term and that term, although small changes, they are equal, and we do not know the magnitude, we have no idea of the magnitude. So we, okay, so in that case by comparison what happens is this term has one d xi I, one d alpha I, whereas this term has d alpha I twice, and so we drop this term over here, okay. In case you are wondering, by comparison if you see there might be a doubt why we dropped this term, okay, I just wanted to say that in the beginning. Now where we are at, we are at this point where using Gauss-Kodazzi relations we came up with our expression for strains, okay. One statement I would like to make about the Gauss-Kodazzi relations is this. I am taking this straight from the book by Harry Krauss, okay, which is thin elastic shells. Now it says that if E, G, L and N are given as functions of the real curvilinear coordinates alpha 1 and alpha 2 and sufficiently differentiable and satisfy Gauss-Kodazzi conditions. okay, with E positive and G positive, okay, and it is implied that F is equal to M is equal to 0, okay, then there exists a real surface which has its first and second fundamental forms given by I is equal to, or 1 is equal to d alpha E d alpha 1 square plus G d alpha 2 squared, and the second fundamental form is L d alpha 1 squared plus N d alpha 2 squared. Okay. So Gauss-Codazzi, if you find a certain A1, A2, R1 and R2 and they satisfy the Gauss-Codazzi relations, then that means it is a real surface. That is what this is saying. Okay. They are like compatibility conditions, and because F and M are 0, what that means is that principal lines of curvature are the parametric lines. Which suits us fine because we are dealing with surfaces of revolution. Surfaces of revolution. Okay. So, if principal lines of curvature are not the parametric lines, there are more general Gauss-Codazzi conditions, which we do not need here. Okay. So, if Gauss-Codazzi conditions are satisfied for a certain A1, A2, R1, R2, that means it is a real surface. That is all I wanted to say in this context. Now, we have found our strains. Okay. The next step is what we call the love simplification. Okay. Now, what is this? So, we are dealing with thin plates or shells. Okay. Now, thin plates you will see as part of automotive bodies. Okay. Bodies of washing machines, aircraft industry, okay, and so forth. Okay. Similarly, shells. Now, thin shells and plates are of interest because they vibrate a lot, okay, and they have resonances in the low frequency range or in the audible range, human audible range. Okay. So, thin shells are of interest. If they are thick, they are not so much of interest because they do not vibrate so much, nor do they make a lot of noise. Okay. So now if I have a thin shell, so I am first drawing it more or less to scale, let us say, and then I will draw this exaggerated. So this is h, suppose this thickness is h, and I will draw it exaggerated. Okay, this is my h now, and this is the middle surface. Okay. Then you can always represent, let us say, the axial movement. There is an axial movement, suppose. You can always represent it as a movement or displacement of the middle surface u and a linear slope, okay, z times beta. Okay. Beta is the rotation of the section. We will see a little more of that. Beta is the rotation of the section, z is the z axis or the alpha 3 axis, Okay. So the u, okay, as a function of, let us say, x comma z, or u as a function of alpha 1 and alpha 3 can be represented by u, small u, let us say this big U, small u, which is purely a function of alpha 1 plus alpha 3 times beta, which is also purely a function of alpha 1. Okay. And this you can do provided in the thickness direction you are thin, Okay. If this is truly thick, suppose this is no more the amplified version, then anything could happen in the middle. Okay. So you can no more say that it is a linear dependent term. Okay. But because it is thin, we are doing this additional approximation. So what now happens in love assumption is that the big U1, alpha 1, alpha 2, alpha 3 is going to be small u1, alpha 1, alpha 2 plus alpha 3 beta 1, alpha 1, alpha 2. So now u2 similarly can be written as equal to small u2, now only on the middle surface, plus alpha 3 beta 2. Okay. Other than alpha 3, everything else is a function of alpha 1 and alpha 2 only. Okay. Alpha 3 comes in explicitly. Then because it is thin, u3 in the alpha 3 direction is uniform across the thickness, so it will be given by u3 alpha 1 alpha 2. So there is no change. So in the thickness direction, this whole thing moves in union or in unison. Okay, there is no change in the thickness. Okay. As a result, immediately epsilon 33 is 0. Epsilon 33 is 0. Okay. Now, what has happened here is that earlier we had 3 displacement variables unknowns, u1, u2 and u3. But now we have u1, u2, u3 that are functions of alpha 1, alpha 2, plus now we have beta 1 and beta 2. So we have moved from 3 unknowns to 5 unknowns. Okay. So now we have to find an expression for these. Okay. Now in the level of the theory we are going to deal with here, okay, that means the level of approximation, the level of accuracy, we are going to deal with here. We are going to set epsilon 1 3 the one vertical shear strain to 0 and epsilon 2 3 the other vertical shear strain to 0. Okay. So along with this, what we have epsilon 3 3 also equal to 0. Okay, so what we will be left with is epsilon 1 1, epsilon 2 2 and epsilon 1 2. These are not equal to 0. Okay. So now the beta 1 and beta 2 definitions will be acquired by setting epsilon 1 3 and epsilon 2 3 to 0. We will get the definitions from there. Okay. We need two more equations to find beta 1 beta 2. This provides us the condition to find beta 1 and beta 2. Okay. Now one more thing. This theory is going to have discrepancy. Okay. This is an approximate theory. In this theory of thin shells and plates, or thin plates and shells. And so we need to know what is the level, or where are we wrong and where is it correct. So we need to look at this inconsistency is a better word, inconsistency. It's an inconsistent theory. Okay. So let us see what is this theory, and we look at it through an example which is an Euler Bernoulli beam. Euler Bernoulli beam theory. Okay. So what is the displacement form? If you have a Euler Bernoulli beam, okay, and that happens to be the z direction, okay, and this happens to be the x direction, and into the plane, into the board is y direction. Okay. The axial displacement u, capital U, a function of x and z, is now broken into u, a function of x alone, plus a z times beta. Okay. Just as we spoke about this right in the beginning. Okay. Then the y displacement is 0 exactly. Okay. And the transverse displacement w of x comma z is w of x. That means this displacement is the same all along z direction. Okay. As a result, what happens? As a result of this, epsilon yy is 0. Okay. Then what are we left with? We are left with epsilon xx, okay, and epsilon zz is 0 from here. Okay. Then we have epsilon xz, epsilon xy and epsilon yz. Okay. Now these two are also 0 because there is no y displacement. Okay. So now we have to look at these two. We have to look at these two. Okay. So if we write the Hooke's law, epsilon xx is 1 over e sigma xx minus mu sigma yy plus sigma zz, okay. Epsilon yy is equal to 1 over e sigma yy minus mu sigma xx plus sigma zz. Epsilon zz is equal to 1 over e sigma zz minus mu sigma xx plus sigma yy. Okay. Now if we use in here the fact that epsilon yy is 0 and epsilon zz is 0, okay, what do we get? We get sigma xx will be equal to e 1 minus mu by 1 plus mu into 1 minus 2 mu into epsilon xx, okay. Then sigma yy will be equal to e by 1 plus mu into 1 minus 2 mu into mu times epsilon xx, and sigma zz is equal to e over 1 plus mu into 1 minus 2 mu into mu epsilon xx, okay. Now in the Euler Bernoulli beam theory, okay, we use sigma xx is equal to e epsilon xx, if you recall, and we set sigma yy equal to sigma zz equal to 0. Okay, so there is an inconsistency. There is an inconsistency, okay, and this kind of is acceptable for a material which has mu equal to 0. If mu is 0, you will find that these are the values you arrive at, okay. It's pointing to a special material with mu equal to 0, okay. So that is one level 1 inconsistency. That means the choice that comes up for sigmas, okay, are different from the choice we actually make, okay. Sigmas that arrive from a choice of epsilons, okay, are different from the final choice we make. That's one inconsistency, okay. So if how will you make it consistent? How to make it consistent? Okay, the way to make it consistent is, because one side says they are 0, if you can find conditions where they are small, okay, sigma yy and sigma zz values are small, then you have found the conditions to make it consistent, okay. So this is one inconsistency. Now the other is this, okay. We were finally left with what? Epsilon xx and epsilon xz, okay. But you see now with epsilon xz what happens? Epsilon xz is given by what? Del u del z plus del w del x. Okay, and this big U was what? Small u plus z beta. Okay, and small u was function of x, z is z, and beta is a function of x again. Okay, so this is equal to del by del z u x plus z beta of x plus del w by del x. Okay. Now this is not a function of z, so what I get is epsilon xz is equal to beta plus del w by del x. Okay. Now here we are going to set epsilon xz to 0. Okay, we are going to set epsilon xz to 0. We are going to set shear strain to 0. Okay, that gives me beta is equal to minus del w by del x. Okay, and so for pure bending, which is what Euler Bernoulli beam is, for pure bending, that means this axial displacement is 0 throughout. Okay, then my capital U is equal to minus z del w by del x, del w by del x. Okay. Now if epsilon xz is set to 0, okay, as is the assumption in Euler Bernoulli beam theory, then sigma xz is g times epsilon xz, and therefore sigma xz must also be equal to 0. Okay, but now watch, if we use the equilibrium conditions from elasticity, okay, then we get sigma del sigma xx by del x plus del sigma xz by del z equal to 0. Okay, sigma x is what? Sigma xx is E epsilon xx, and epsilon xx is del u del x. Now u in this form, del u del x, so that is equal to minus Ez del 2w del x square. Okay. Okay, so now we will replace this with our familiar m over ei expression from undergraduate. So what I have here is minus E z del x of m by ei plus del del z sigma xz equal to 0, okay, or del sigma xz by del z is equal to Ez del del x m by ei, okay. Now what happens? If I integrate with respect to z, okay, then my sigma xz becomes del by del x, okay, m z square by twice I plus g of x, okay, and say at z equal to plus h by 2 my sigma xz equal to 0, then I have 0 is equal to del by del x m by I h square by 8 plus a g of x is 0, right. Then that gives me a definition for g of x as minus del by del x m over I h square by 8, okay. So finally sigma xz becomes 1 by twice I del m by del x z square minus h square by 4, okay. So it's a parabolic, you must have seen this before, okay. So across the cross section this has a parabolic behavior, but earlier we said as epsilon xz equal to 0 sigma xz must be equal to 0. No, that's not the case, okay, that is not the case. So this is also an inconsistency, okay. So how do you make it consistent then? Then here also you find a condition, it will come as a condition on geometry. So you find a condition, okay, you find a condition or you find conditions such that sigma xz is also a small quantity, okay. Now let us just take a simple example, a static example. We will take a static example, okay. I am taking this example from Shames and Dim, book by Shames and Dim. I think it's called FEM and energy methods, something like that, energy methods. Okay, I am taking this example from there. So the example is this: you have a simply supported beam, okay, and you load it with a uniform load, uniformly distributed load, you load it, that is Q of x. Okay, and I have this non-dimensional parameters which is xi, let's say is x by L, and eta is z over h. H is the thickness, okay, that is z, this is x. Okay, then sigma xx, the normal stress is given by minus q L square h pi twice I, okay, xi square minus 1/4 eta plus h over L whole squared 2/3 eta cube minus 1/10 eta. Okay, this is a full elasticity solution. Elasticity solution. Okay. Similarly, from the same full-blown elasticity solution, you get sigma zz given by minus q L square h by twice I h by L whole squared into 1/3 eta cube minus 1/4 eta plus 1 by 12, and sigma x z is given by minus q L square h by twice I h by L 1/4 minus eta square into z. Okay, so you can see now, if you do this solution from just Euler Bernoulli theory, you will find, of course, zz is 0, okay, and xz is whatever it is. Okay, so now when do the two theories meet? So here the xx is without this term. Okay, so when do the two theories meet? When h by L is small. When h by L is small, this term is 0 or negligible. It is equal to this which comes from Euler Bernoulli beam theory. This term goes to 0, which Euler Bernoulli beam theory says, and this term also becomes small such that elasticity and the beam theory come together. Okay, so that is the condition. So that means what? The thickness should be much smaller than the the other dimensions of the structure. Okay, so which suits our thin plate study. Okay, so if our structures are thin enough, then the Euler Bernoulli level of approximation is good. Is good. Okay. When it comes to two-dimensional structures or plates, actually, the same level of approximation, that is of setting the shear strain to 0, and shear stress not 0, and the normal stresses in the z direction and normal strains z direction both to 0, okay, this is called Kirchhoff plate theory. Okay, Kirchhoff plate theory. So we are going to work at that level of approximation with plates and with shells. Okay, I am running out of time, so I will stop this lecture here. We will continue from here.